Hello, everybody. Mr. Klein here, in a hat. It's fun. I'm running out of hats. If you have some hats that you'd like to donate to my cause, send them to this address right here. And on with today's lesson. Today we're going to be talking about section 3-4, the derivative function and the power rule. I want to begin by talking about what we talked about a couple classes ago, which was the derivative at a point. The idea is this. You got a function, and you got a point. We'll call that C. Recall that C stands for constant. By the way, you don't need to write this down. You've already written it down once. Just watch me for a second. You'll see where I'm going. Well, we know that if this is C, boom, boom, then right here we have f of C, and we want the derivative at that point. And our approach went something like this. We define a second point as x, comma, f of x. And we calculate the slope of the line that passes through those 2 points. And the slope of that line is f of x minus f of c. That's like our change in y, divided by x minus c. That's like our change in x right here. And the other thing that we talked about is that if you want the actual value of the derivative at this instant right here, what we have to do is pick up this point and drag it back towards this point. How close? As close as we can possibly go. In other words, we want to take the limit as x approaches c. Now, I would say that this way of finding derivatives is dumb. And the reason I say this is dumb is because it only gives us the derivative at one single stinking place, right? So today, I'm going to show you a way to find the derivative at every single point on the entire curve all at once. It goes like this. Now I want you to write this down. Suppose instead of defining a constant like c, we define this as x, which would make the y value f of x. And then suppose that we take the x value and we change it by a little bit. How much do we want to change it by? Let's suppose the amount that we change it by is, I don't know, the change in x. Well, if that's the change in x, boom, 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 then this point right here would be x plus a little bit more. And then over here, this would be f of x plus a little bit more. So we have 2 points, this one and this one, and we find the slope of the line that goes through them, which, as we saw in the last example, is just this change in y divided by this change in x. So that would look like something divided by something. Okay, where the, let's see, the change in y would be this. Subtract this. The denominator would just be this little yellow region, which is just the change in x. All right, now check it out. We're going to write an equation for f prime of x, where this right here would give us a number, a value. You know, like the derivative is 6. This is going to give us a function. It's going to give us the derivative is always equal to 4x minus 7 or something like that. All right, so check it out. Now, one thing you need to know is that mathematicians, very, very, very lazy. In fact, we are so lazy that we are unwilling to write change in x. So for reasons that I've never really fully understood, instead, we make that an h. So this is going to say f of x plus h minus f of x is divided by h. The way that we get the actual derivative is also like the other one by taking a limit. And just like the other one, we have to take the point that's up here and we have to drag it back towards here. Now, the way that we do that is by making this interval right here as small as possible. So in other words, the way that we're going to do that is we're going to make the value of h, this right here, we're going to make it go to 0. So we get the limit as h goes to 0 of this will give us our derivative function. If this makes no sense to you, don't worry, it will as soon as we do an example. And I just happen to have an example waiting for us right here. We want the derivative function of f of x is equal to x squared minus 4x plus 3. And this, correct me if I'm wrong, is a quadratic. And if this is a quadratic, that means it has a degree of 2. And we know that when we get the derivative equation, when we're all done here at the end, the derivative is going to have to be linear. In fact, if I asked you to draw a picture of the derivative, you could probably do that, right? This is the original function. Couldn't we say, well, this original function is decreasing, and then it changes directions here, and then it's increasing? So the derivative function would have a 0 right here. It would be negative on this side and positive on this side, and it would be linear. So the derivative equation is going to look something like this line here. And just keep that in mind for when we are all done. Here we go. I've broken this up into a 4-step process. And the first step, frankly, the hardest step, is to calculate this, f of x plus h. So that would mean we take our f function, and everywhere that we see an x here and here, we replace it with a space. And the thing that goes in that space is x plus h. And then we multiply that out. Let's see, this first one would give us x squared plus 2hx plus h squared. And then the next one would give us minus 4x minus 4h, one of my favorite clubs, plus 3. So there's the answer to step 1, complete. Step 2 is to take what we did and subtract f of x from it. Once we do that, it'll give us the entire numerator of the expression. So I'm going to take this and I'm going to subtract f of x, which means that I'm going to subtract an x squared. Notice that I've got one already. I'm going to subtract a negative 4x, so that means I'm adding a 4x. And then I'm going to subtract a 3. So these 1, 2, 3 terms, they're going to cancel, and we're left with 2hx plus h squared minus 4h. All right, next step. We want the entire fraction. So we're going to take what we have and we're going to divide it by h. So we take this term, and this term. We divide by h. That drops the power on h for each term. So we have 2x plus h minus 4. And then the last step is to take the limit as h goes to 0. Now, if we do that, what we're going to end up with here is 2x plus plug in a 0 minus 4, which means that the derivative function is equal to 2x minus 4. How is this helpful to us? Well, it does a couple of things. First, I can now find what the rate of change of this function is at any point. For instance, right here, this is when x is 0. So if I wanted to know the slope of that line, I could just plug in 2 times 0 minus 4 is equal to negative 4. So that's how this is useful to us. Also, note that this linear function looks just like the derivative function that we drew right here, right? It's got a y-intercept of negative 4. It's linear, boom, 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 boom. And when you plug in, what would that be? 2. X equals 2. You get 0. So it works. Let's do another one. This time we're doing f of x is equal to x cubed. See if you can remember the first step. If not, look back at the last page of your paper and see what the first step is. Should look something like this. When you're doing x plus h cubed, it's just an algebra thing. I think it's probably not a good idea to do x plus h times x plus h times x plus h. You are likely to make mistakes. I would encourage you to use what's called the binomial theorem. The binomial theorem goes like this. I'm writing out Pascal's triangle. Recall that on Pascal's triangle, each row, the values are equal to, will this thing stop being kooky? There you go. The values are always equal to the sum of the two values above. So like right here, I got a 3 by doing 1 plus 2, then another 3 by doing 2 plus 1. So the next row would go 1, 4, 6, 4, 1. And if we wanted to go one further, it would go 1, 5, 10, 10, 5, 1. Notice that they're always symmetric. If you don't remember, the way this is helpful is that if we wanted to expand this guy, we could say that the coefficients are going to be the things in the row with the 3, because this is degree 3. So our coefficients will be 1 dot dot plus 3 dot dot plus 3 dot dot plus 1 dot dot. And then our powers are just going to be x to the third, x to the second, x to the first, x to the 0, and then h to the 0, h to the 1, h to the 2, h to the 3. All right. So that's probably the trickiest part. See if you can remember the second step, what we do next. That's right. The next thing we do is we subtract off f of x. So if I subtract an x cubed, we are left with 3x squared h plus 3xh squared plus h cubed. See if you can remember the third step. You do need to know it. The third step is to divide by h, which is going to knock the powers down on each one of these. So we get 3x squared plus 3xh plus h squared. See if you can remember the final step. And that final step is to take the limit as h is approaching 0. which would give us 3x squared plus 3x times 0 plus 0 squared. Therefore, our derivative function is going to be 3x squared. Notice that once again, the power dropped by 1 when we took the derivative. All right, I'm going to be quiet for a minute, and I would like you to take a crack at the next example. When you're done, unpause the video. All right, here's the answer. Pause your video again if you got it wrong, and then take a look at my work. Otherwise, let's move forward. This is pretty laborious too, right? Wouldn't we like to have a faster way of doing this? Well, some of you may have noticed that there's a pattern from here to here, and then from here to here. Notice that the number that was in the exponent now ends up in front. And the exponent decreases by 1. And you'll note that the same thing happened right here. We had x to the 4th, and it became 4x to the 3rd. And in fact, if you look back at the last page, same thing happened here too, right? The x squared became a 2x, or a 2x to the first power. And then the 4x, the 1 in front kind of like came down and multiplied, and then the degree on the x reduced by 1 to give us x to the 0, which just gone. All right, so we found this pattern, right? I will allow you to use this pattern if you can prove it with me. Here we go. So let's suppose that we have f of x is equal to x to the n. Based on our rule, we would conclude that we're going to get f prime of x is equal to, move the n in front, times x to the, knock the power down by 1, and we would get n minus 1. Let's see if we can make this happen. All right, here we go. So this would be x plus h to the n power. And if we expand that out, let's see, we'd have x to the, that first power is always n, right? Plus the second coefficient is always n, so this would be n times x to the n minus 1 times h plus a whole bunch of junk is going to happen. At the very end, we would have an h to the nth power. Now, the only term that has no h's is going to be this one right here. And that's important, because look what's going to happen. Step 2, we subtract x to the n. These two go away, and look what we're left with. N times x to the n minus 1 times h plus a bunch of gobbledygook. So that when we divide by h, right, that's the next step, is to divide this whole thing by h, what we are left with is this term. The h goes away, but all the other terms, which we can't see here, are going to have higher powers of h. The last one, I guess, would be n minus 1 now, but even that doesn't matter. The point is that when we take the limit as x goes to 0, all of these go away, and we're left with this fact. If a function is x to the n power, as long as n is not 0, bad things happen with 0, then the derivative will be n times x to the n minus 1.